Hello, good people. In front of us, we have May 2023, Paper 2, Timezone 2, question number 3. You may pause the video and then try it first before we discuss it together. Okay, this question, we have an experiment with the bacteria. The population of the bacteria can be modeled by the function P of t is equals with 1200 times k to the power of t, where t is more than 0. T is the number of hours and k is positive. Write down the value of p0. When the p is equals to 0, not p equals to 0, when the t equals to 0 here, t is equals to 0, meaning the time is 0, k to the power of 0 is 1, so p0 is equals to 1200. Okay, that's p0. Interpret the value. This means, it means when the time is equals to 0, the population is 1200. Or you can also say the initial population of the bacteria is 1200. You can also write it that way. Okay, next, 3 hours after the experiment, the population of the bacteria is 18,750. Find the value of k. Okay, I will make this a little bit smaller so we have more space to work on. Okay, there you go. Okay, so for question B, I'll write it here. Question B. The population is 18,750 is equals with, when the time is 3 hours, so it means 1200 times k to the power of 3. Like that. Okay, so we will have k to the power of 3 is equals with 18,750 divided by 1200, and then k is equals with the third root of 18,750 divided by 1200. Let's input this to our calculator. We have math, third root of, okay, we have 18,750 divided by 1200. Enter. 2.5. So we have k equals to 2.5. Okay, C. Find the population of the bacteria 1 hour and 30 minutes after the experiment began. Question C. So 1 hour and 30 minutes is t is equals with 1.5. Remember, not 1.3 because 30 minutes is half hour. So the population, so p 1.5 is equals with 1200 times k is 2.5 to the power of 1.5. The time is 1.5 is equals with 1200 times 2.5 to the power of 1.5. We will have 4743.4. 4743.4, blah blah blah. We have to make this into 3 significant figures, so approximately 4,740 bacteria, and there you go. This is P 1.5. Okay. Next, the scientists conduct a second experiment with different species, and then the equation is St is equals with 5,000 times 1.65 to the power of t, where t is more than 0. Find the value of t when the populations are equal. So question C, Wait, I thought that one is question C. No, question D. My bad. Sorry. Question D. I'll do it here. Question D. They have equal, so it means the first equation, which is 1200 times 1.5. 1200 times 2.5. 2.5 to the power of t is equals with second equation, which is 5000 times 1.65 to the power of t. Now, to do this equation, you have two ways. You can draw it. You can draw it here, y equals 2. Then you find the intersection, or you can use the numeric solver in your calculator. So you go to numeric solver, press math, go to numeric solver, enter, and then you input your equation. I already input the equation. The first equation is 1200 times 2.5 to the power of x, not t, because our calculator recognizes x, not t. Second equation is 5000 times 1.65 to the power of x. And then press OK, and then you solve it, enter like this. Okay, so we have x equals with 3.4345. So we have t equals with, what was that? 3.4345. 3.4345 blah blah blah, or t is approximately 3.43 hours. Wait a minute, what should we answer this on? Find the value of t. Okay, find the value of t where the two population are equal. Okay, it doesn't ask us for the nearest minute, so this one is okay. E, it takes 2 hours and m minutes for the bacteria second experiment to reach 19,000. Find the value of m, giving your answer as integer value. Now, this one we have to find it in minutes. Okay, let's do question E here. Question E. So the population is 19,000. So 19,000 is equals with this one, 5,000 times 1.65 to the power of t. Now you can use another numeric solver, but let's just use algebra now, yeah? So we divide both of them by 5,000, so we have 19,000 divided by 5,000 is equals with 1.65 to the power of t. Once again, you can use numeric solver. I just want to use log. Now you can use logarithm. The base is 1.65, so we have log. The base is 1.65. We have 19,000 divided by 5,000 equals to t. So t is equals to, let's input it to our calculator. Okay, go to math, then go to log base. Where is our log base? There you go. Log base. The base is 1.65. This one is 19,000 divided by 5,000. You can just do 19 divided by 5, yeah, because the 0 will cancel out, but that's okay. We have 2.6658 2.6658 blah blah blah. Remember, the one that we look for is the value of m, which is the value to the nearest minute. M is the nearest minute, so it's 2 hours and blah 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 minutes. What is the blah blah blah? Yeah, you can look at this, which is 0.2 is 2 hours, and then 0.6658 blah blah blah. That's the minutes. That's the m. Okay, but we have to find the m. So m is equals with 0.6658 times 60. Why 60? Because 1 hour is 60 minutes. So m is equals with, so we input it to our calculator. You can just use the answer. Second, the answer, we minus it with 2. Why we minus it with 2? Because we want to find this one, 0.66 blah blah blah, and then we multiply it by 60. What do we got? We have 39.95. M is 39.95, blah blah blah. Remember, to the nearest minute, so M is approximately 40 minutes. Okay, what's question F? Okay, question F. The bacteria in the second experiment are growing inside the container. The volume of each bacteria is this. It's very small. And then the available volume of the container is this. So we have to find how long it will take for the bacteria to fill in the container. So basically we have to find the number of bacteria, maximum bacteria first. We just divide the capacity. So we have to find the capacity of the container. So F. So this is maximum bacteria we can have will be, just write max, so 2.1 times 10 to the power of negative 5 divided by 1 times 10 to the power of negative 18. Let me repeat. It's basically the volume of the container divided by the volume of the bacteria. Then that will give us the number of bacteria we can have. We will divide this. So we have 2.1. Let's put it in bracket. 2.1 times 10 to the power of negative 5 close bracket divided by open bracket 10 to the power of, we just ignore the the one, 10 to the power of negative 18. Okay, close bracket, enter. We have 2.1 times 10 to the power of 13, which is 2.1 times 10 to the power of 13. This is the maximum number of bacteria in the container. So we will input this. Same method with question E. It's just the number of bacteria, now 2.1 times 10 to the power of 13. So we will have 2.1 times 10 to the power of 13 equals with, what was that? 5,000 times 1.65 to the power of t. Okay, cool, correct. So we divide it all by 5,000. So 2.1 times 10 to the power of 13 divided by 5,000 is equals with 1.65 to the power of t. We will make the log again. So t is equals with log, the base is 1.65, and then the number here is 2.1 times 10 to the power of 13 divided by 5,000. Okay, so t is equals with, let's input it to our calculator. Okay, we have log base, math, go to log base. Log base, we have 1.65. Then this one is 2.1 times 10 to the power of 13. Oops, sorry, 13 divided by 5,000. Enter. 44.248. 44.248 blah blah blah. So t is approximately 44.2 hours. Wait, let's check, is that the one that we require to answer? Determine how long take for, okay, cool. It doesn't have to be in the nearest minute, so 44.2 hours should be okay. So that's for this question. I hope this thing helped you. Please leave a like or comment if you have another method. See you again in another video. Thank you.